Hi everyone, I would like to welcome you all to the mechanics lecture series. So as you know, it is a common module. That's why we have a code ETC. It is a common module for Bachelor of Engineering Technology degree program, right? So it is a 3-credit module. Usually we have practical sessions also, but in this case I'm not sure whether we will be able to conduct the practical sessions. So let's see how this COVID case is going on. If any case, if we can start physically, definitely we will arrange some practical sessions, but for now I don't think it will be feasible. So it is a 3-credit module. If the COVID case continues, you all know that you will get 70% for your assignments and 30% will be allocated for the final end semester examination. So since it is a 3-credit module, it has a large impact on your the semester GPA. So if you do well in this subject, which means that it will help you to have a very healthy GPA at the end of your semester, right? So if you take the mechanics, it is we can say it is a core module, or we can say it is a pillar. It's one of the pillar subjects in engineering technology or in engineering. So it applies everywhere. It applies in civil engineering, it applies in automobile engineering, or it applies in the energy and environment area. So it is, the mechanics is everywhere. It is a core module. That's why understanding the concept of mechanics is very important. And I would say that mechanics is if you look at the results of the previous, I mean your seniors results, you would see the results are quite in the lower side, which means that it is a difficult subject for not only technology students, even for the engineering students, right? So if you understand the concepts well, it will be a easy subject, right? So we will try to understand the concepts, right? So I'm Dr. Asankar from Department of Civil and Environmental Technology. So in the first lecture, we will discuss about some of the fundamental concepts. In this lecture, I will cover for the first 2 weeks of your lecture materials. So the first question is, what is mechanics, right? Mechanics is a branch of the physical sciences that is concerned with the state of rest or motion of bodies that are subjected to the action of forces, right? So mechanics describes and predicts the condition of rest or motion of bodies under the action of forces, right? So this rest means it is in equilibrium, or the rest mean it is in a static state, or which is not moving, or motion of bodies under the action of forces, right? So in general, this subject can be subdivided into three branches: rigid body mechanics, or deformable body mechanics, and fluid mechanics. But in this lecture series, we will study rigid body mechanics. We will study about the rigid body mechanics, since it is a basic requirement for the study of the mechanics of deformable bodies and the mechanics of fluid, or the fluid mechanics, right? So all you will learn this fluid mechanics, I think at the third, if I remember correctly, you will learn the fluid mechanics in your third semester. So rigid body mechanics is also essential for the design and analysis of many types of structural members, or the mechanical components or electrical devices encountered in engineering or technology. So rigid body mechanics can be divided into two areas: statistics and dynamics. So rigid body mechanics can be divided into two areas. One is static, and dynamics. So statics deal with the statics. Here this one deals with the equilibrium of bodies. This one deals with the equilibrium of bodies, and the dynamics is concerned with the accelerated motion of the bodies, right? So the equilibrium of bodies means those that are either at rest or move with constant velocities. Equilibrium of bodies in mechanics mean the objects either at rest or moving with constant velocity. Okay, so the rigid body mechanics can be divided into two categories: statistics and dynamics. Statics means equilibrium of bodies. So equilibrium of bodies in mechanics means the objects that are at rest or moving with constant velocities. At rest means the objects at the, which means the not moving bodies, right? So, and dynamics means is the objects that which are accelerated motion of the bodies, right? So we can consider statics as a special case of dynamics in which the acceleration is zero, right? So here in this lecture series we will deal with statics and dynamics parts, right? So mechanics have been evolved for ages, right? From Archimedes to the Einstein, right? You all know that Archimedes found the laws of buoyancy and the principle of lever. So all these things comes under the mechanics, right? So simply we are going to learn about the rigid body mechanics, which can be divided into two categories: statics and dynamics. So under this statics, we are going to learn about the bodies which are at equilibrium, which means the objects at rest or moving with constant velocities, right? Okay, let's discuss some of the important concepts in mechanics. First one is particle. You all know that we say a particle has a mass but a size that can be neglected, right? This is usually how we define a particle, right? A particle has a mass but a size that can be neglected, right? If you take a particle, the size of that particle is can be neglected, but it has a mass, right? So this is how we define the particle, right? So in mechanics, even there is a dimension, sometimes we consider them as particle. For example, if you take uh, if you take this if you take this ring, if you consider this ring, we can consider this ring as a particle. Why? If you take this ring, it is subjected to three forces, right? This one, and this one. So all these three forces, if you look at, they will meet at this point. Since all these three forces meet at one point, we can assume the ring to be represented as a particle. So when a body is idealized as a particle, the principles of mechanics reduce to a rather simplified form, since the geometry of the body will not be involved in the analysis of the problem. That is the importance of considering this as a particle, right? So usually, if I repeat again, usually we call a body as a particle when the size of that body can be neglected, right? But in mechanics, the forces acting on that body meets at one point, we can consider that body as a particle because we don't need the geometry of that body to for the equilibrium of this ring or the body, right? So at that sort of condition, we say the body we can assume as a, or the body can be represented as a particle, right? Then the rigid body. Rigid body can be considered as a combination of a large number of particles in which all the particles remains at a fixed distance from one another, both before and after applying a load, right? So if you take if I take uh, this as a rigid body, say this point is A and this point is B. The difference or the distance between the point A and say point B is just a simple x. then the distance between the A and B is, say, just x meters. So now we apply forces on this rigid body. If the distance between A and B does not change or will remain as x under these forces, we call this body as a rigid body. If the distance reduced or increased when you apply forces on a body, then we don't call it as a rigid body. It is a deformed body, right? So when a body, when we apply forces on a body, the distance between any two particles does not change. We call it as a rigid body, right? So but in usually when you apply forces on a body, it slightly change the dimensions, but we don't consider the slight changes, and we assume those type of objects as a rigid body, right? So then concentrated force. Concentrated force represents the effect of a loading which is assumed to act a point on a body. We can represent a load by a concentrated force, provided the area over which the load is applied is very small compared to the overall size of the body. If you take the wheel of a train, if you take the wheel of a train, the contact point between the railway line and this wheel is fairly small compared to the size of the wheel, right? So the force is applied on here, right? So we can consider this force as a concentrated force, right? So when you when the load is applied on a very small area of the body compared to the total area of the body, we call that the force as a concentrated force, right? So these are very important concepts. These concepts will be used throughout our lecture series, right? So try to understand the concept, right? So then it will help you to learn the subjects well. So as I mentioned in our first slide, we are learning concept in our first lecture, right? So let's try to identify the difference between the scalars and vectors, right? I think you already know about these things, but just to remind, scalar is any positive or negative physical quantity that can be completely described by its magnitude. We call it as scalars, right? So no any other information is needed when you consider a scalar, right? If you have only the magnitude, that would be enough, right? For example, if you take the time or the temperature, we say just the 20 centigrade, the magnitude is enough to describe the quantity, right? Physical quantity, right? So the those uh, type of quantities or physical quantities we call as scalars. There is another one we call as vectors. Any physical quantity that requires both magnitude and direction for its complete description we call as vectors, right? For scalars you only need the magnitude, but for vectors you need both magnitude and direction, right? For example, if you take the force or velocity, they are vectors, right? So if you take the force, say F, 20 kilonewton, when you represent a vector, we give the magnitude as well as the direction, right? Direction of the force. But when you say about the temperature, we just give the magnitude of that quantity, right? But in the case of vectors, you need to give both magnitude and the direction, right? uh, Before going through the lecture, I think you need to remind some of the concepts that you learned in the mathematics, right? So these are the important concepts that I listed up. So you need to go back to your mathematics class and remind yourself, right? So try to remind what is the equal vector and what is the equivalent vector, what is the difference between the equal and the equivalent vector, what is the unit vector, what is the position vector, and how we multiply and the division or divide the vector by a scalar, how we can add the vectors, how we can subtract the vectors. So try to revise yourself vector and vector operations, right? So I'm not going to go through all these things. You need to go back to your maths lecture notes and get familiar with these vector and vector operations, right? So usually we denote, we represent the vector using bold letters, or since in books usually use the bold letters, right? But in handwritings you cannot use bold letters. So we simply drawing an arrow, say V is a vector, then we use drawing an arrow above the letter, right? This is how we represent the vectors, right? But in the textbooks, they usually use the bold letters, right, to represent the vectors, right? So whenever you see the bold letter in our presentation, you must remember that it represents a vector. So if it is not a bold letter, which means that just a scalar, right? And whenever I write something like this, you must remember that it is a vector. If I write something like this or something like this, then you should remember it is a scalar, right? So go back to your maths lecture notes and try to get familiar with these vector and vector operations, right? So it will help you to understand the concepts that we are going to learn. Okay, now we are moving to find the resultant force, right? So the resultant force means that, say that if there are two forces, say you have two forces, one is this direction F1 and like this F2. So if you can express F1 force and F2 force using a one force, say something like Fr, so instead of two forces, if you can express these two forces in using one force which has the same effect as F1 and F2, we call it as the resultant force, right? So if there is three forces or four forces, if you can sum up all these forces and express just one force, then we call that force as the resultant force, right? So why we need to find the resultant force, right? It is, rather than dealing with two or three or four forces, right, n number of forces, is very easy to deal with just one force, right? That's why we are interested in finding a resultant force, right? So there are two methods that you can find the resultant force, right? So we are now going to find the resultant force of coplanar forces. Coplanar means that the forces are on the same plane, right? Plane means that if you take x and y coordinates, then x and y plane, the forces on this x and y plane are called as coplanar forces, right? So in the same way, if you take y and z, then the forces on y and yz plane we call as the coplanar forces, right? So forces on the same plane we call as the coplanar forces, right? So as I mentioned, there are two methods, right? First method is using a triangle law or parallelogram law or polygon law, right? So if there are two forces, we can use triangle and parallelogram law. If there are more than two forces, you can simplify it to the triangle and parallelogram law, but you use the polygon law, right? For example, say that you have now two forces like this. So one is this F1, another one is say F2, right? So then how can we use the triangle law to find the resultant force of F1 and F2? First thing that you should do is say this angle is theta 1 and this is theta 2, right? So you draw the F1 force first. So this is the F1 force. This angle is theta 1 with the x direction, right? So this is F1 force. Then at the end of the head of the F1 force, right, you start drawing the second force which has the same direction as the original force, right? So it is in this direction, right? This is the F2 force, right? So this angle is theta 2, right? So this is the first force F1. So at the end of the first force, at the end of the head of the first force, you draw the second force which has the same direction as our original force. Then the third side of this triangle, right? So if you want to make this a triangle, then you should draw from here to here, right? Draw the third side from here to here, right? So the magnitude of this side, if you draw this F1 and F2 to the scale, then the magnitude of this side gives you the magnitude of the resultant force. And this direction, say this is phi, direction gives you the direction of the resultant force, right? This is how you draw the triangle law. You use the triangle law to find the resultant force, right? So first step is draw the first force, then at the end of the first force draw the second force, then the third side gives you the direction and the magnitude, right? So the direction is in this way, right? Not in this way, right? Say this is A, this is B, and this is C. The resultant force we say Fr. So Fr is in the Fr is in the so Fr is in the this direction, right? So this is how you draw the uh, triangle law, right? So in the same way, you can draw a parallelogram for these two forces. Say this is our two forces. Say this is our two forces. This is F1 and this is F2. Then you can draw parallelogram for this one, right? So draw the parallelogram. You draw a parallel line to this one which has the same length as this, then draw a parallel line to this one which has the same length as this one. So this one and this one are parallel, this one and this one are parallel. Then this diagonal gives you the resultant force. Say it is Fr, right? So if you know this theta 1, this one, and this direction, say phi, gives you the direction of the resultant force, right? So this is how we use the parallelogram law or triangle law to find the resultant force, right? So say now you have more than two forces. Say now you have another force in this direction, F3. Then how can you draw? Then it is not the triangle, it becomes a polygon, right? So then I delete here. Then you start from here and draw the third force, right? Say this, then this one gives you the resultant force, and this is the direction of the resultant force, right? So now it is not a triangle, it is a polygon, right? So this is how we can use the triangle or polygon to find out the resultant force of coplanar forces, right? So this is the first method, right? So you will understand it well when we are discussing the example, but this is just the theory how you can use the triangle or the polygon or the parallelogram, right? So there is another method. This is the first method. There is another method that we call it as the resolve into rectangular Cartesian coordinates, right? Resolve means you divide this force into two components, right? Resolved into rectangular, which means that dissolved into two components which are perpendicular to each other. That's what rectangular means, right? And Cartesian coordinates, right? So Cartesian coordinates, now we are dealing with coplanar forces, say x and y. So express the coordinates in I and j terms, right? I and j terms, right? Say now you have a force F like here, right? Say this is our x direction, this is our y direction. You have force F, right? So if you resolve this into x direction, the component of the uh, F force in the x direction is say Fx. The fraction in the y direction we can say Fy. The resolvent into the y direction is Fy. To the x direction is Fx. Then the vector F, force F we can say as Fx times I plus Fy times j. This I is the unit vector along the x direction and j is the unit vector along the y direction, right? So if you remember that I told we use bold letters to demonstrate or illustrate the vectors, but if just the simple letter to illustrate the magnitude. So if you look at here, you can see that this one is a bold letter, right? This is also bold and this one also bold. So which means these are vectors. But here it is not bold, which means that this is just the magnitude, right? So here that's why I use the arrow above the F to indicate that F is a vector, but here it is Fx is just the magnitude and Fy also magnitude, and I and j are vectors. I is the unit vector along x direction, j is the unit vector along y direction, right? So for example, if I express a force, say I say my force F is equal to 10I plus 7J, then 10 is the Fx and 7 is the Fy, right? So this 10 is the resolvent of this force F into the x direction. So the magnitude is 10 and the magnitude of the resolvent of this F force into y direction is 7, right? So then if I want to find the magnitude of the F, then how can I find? I should use Fx squared, right? Fx squared, say I want to find the magnitude of F. Now square root of Fx squared plus Fy squared, right? Why? So this is the magnitude length of this side, right? So it is Fx squared plus Fy squared square root, right? So magnitude of this case is equal to 10 squared plus 7 squared square root, right? So if say this angle is theta, then you want to find the direction, then tan theta is equal to this length, which means Fy 7 divided by this length, which means 10, right? So theta is equal to tan inverse 7 over 10, right? So whenever you have a force F, you can express that force in Cartesian vector forms like this, right? So if you have a vector F, you can express that force in Cartesian vector forms as Fxi plus Fyj, right? So then if you have say there now if you have two or more vectors, now you have say this is my x and this is my y, this is f1 and this is f2. Say this f1 is equal to a1i plus a2j. This is equal to say a1 plus say b1j, and this is a2i plus b2j. Now we want to find the resultant force of F1 and F2. The resultant force, if I say Fr is equal to vector summation of F1 plus F2. This is not the algebraic summation. This is the vector summation, right? That you should remember, right? So this is the vector summation, right? So F1 in my case is A1i plus B1j plus F2 is A2i plus B2j. Right now I should take I terms together, then it become A1 plus A2i plus B1 plus B2j, right? So this is the resultant force in Cartesian vector form, right? You should remember that F1 plus F2 means just the vector summation. These are vectors, right? Not algebraic form, right? So you cannot just say Fr is equal to A1 plus A2 plus B1 plus B2. This is wrong, right? So it is just a vector summation. So you should add all the I terms together and all the j terms together, right? So let's see some examples, right? So example 1, it tells the screw eye. So this is the screw eye, right? In figure subjected to two forces, force F1 and F2. So determine the magnitude and direction of the resultant force. We need to determine the magnitude and the direction of the resultant force. So we have two forces, F1 and F2. You can see that they are coplanar forces. So they are on the same plane, right? F1 force is in this direction, which is 15 degrees from the x-axis. If we take this as the x-axis and this as the y-axis, F1 is in the 15 degrees away from the x-axis and F2 is 10 degrees away from the y-axis, right? So we need to find the resultant force. So as we learned in our previous slide, you can use either triangle law or you can resolve the forces into x and y direction and solve the problem. So we'll use the first method. We'll use the first method to showcase how we can use the triangle law to solve this type of problem, right? So as we know, uh, if we draw the force triangle, which means that, say this is the our x-axis. Now our F1 force in this direction, this is 15 degrees, right? So you draw the one side of the triangle is equal to the F1 force. Then you have the second force F2. You should start drawing the F2 force from this point, right? Say this is A. If we take this as A and this point as B, then we know that this is in this direction, right? If we take this, so if we take this, you know that the angle between two forces is this is 90 minus 10 plus 15 is 25, so it is 75 degrees, right? So from this force we take from here, it is 75 degrees. So your force F2 is, say this is your F2 force, right? So I say it is C. So you shown that these two forces by the two sides of the triangle. Then the third side of this triangle, we take the third side of this triangle, it gives the direction and magnitude of the resultant force. This is the force Fr, right? So this one is 100 and this is 150 Newton, right? So if we take this angle as theta, right? So this angle, this is the direction of the resultant force, and this one gives the length of this triangle. If we draw it to the scale, gives the magnitude of the resultant force, right? But we haven't drawn this to the scale, right? So we are going to use the cosine and sine laws to find the magnitude and the direction, right? So this is how we draw the force triangle, right? So you take the F1 force and draw it. You illustrate the angle and the magnitude of the force. Then you draw the second force where it is, where the first is starting from the point where first force stops, right? You shown the magnitude and the direction. Then the third side of the triangle gives you the direction and the magnitude of the resultant force, right? So if you go to the next slide, it is, yeah, the force triangle is like this, right? So you can use the parallelogram law also. If you draw the force parallelogram, it will be like this, right? So this is the resultant force, right? So we know that this angle is 15, right? So this is this angle. If we take this angle, we know it is 75, right? So this angle should be 115 degrees, right? So we say this angle is theta, right? So, and this one is 65 degrees, right? This, and you know that this is a 65 degrees, right? So then we want to find the magnitude and the direction of the this resultant force, right? If we find the theta, we know the direction, right? So first let's see how we can find the magnitude of this resultant force, right? So we know there are laws called sine and cosine and sine laws, right? I think you have learned this cosine law in your mathematics class, right? So if you apply that cosine law, right, it tells that uh, cosine law is equal to if we say, if you want, you have a triangle something like this, say then this is A and this is B, the length of this side is A and length of this side is B, and this angle is theta, then the length C, if the length of this side is C, then we can say C squared is equal to A squared plus B squared minus 2AB cos theta, right? So the length of this side C is equal to square root of A squared plus B squared minus 2AB cos theta, right? So the length, if we find the length of this side, which means that is the magnitude of the resultant force, right? So we know the length of this side, it is 100, right? So 100 plus 150, that is the length of this side, right, minus 2 times A is 100 times 150 and cos 115, this angle is 115, is equal to the square root of that is equal to the resultant force, right? So if you solve this one, you will get the resultant force is equal to 212.6 newtons, right? So now we found the magnitude of the resultant force, right? We know force is a vector, right? So we found the magnitude. So still our answer is incomplete. Why? Because force is a vector. So if you want to uh, indicate the vector, you should have both magnitude and the direction. So we found the magnitude. Then we need to find the direction of this force, right? So we can say, how can we find the direction of this force, right? So if we find this theta angle, we know the phi, can say the angle the resultant force makes with the x is equal to phi. So phi, we can say phi so we can say 5 is equal to 15 degrees plus theta, right? So if you find the theta, then we know the direction of this resultant force, right? So there is a law called sine law, which gives which tells you the ratio between the sides and its uh, angle, right? So if we express the sine law, the 150 divided by this angle sine theta, the length of this triangle, and divided by the opposite angle, right, is equal to 212 divided by sine 150, right? So from that you can find the theta, right? So theta is equal to 39.8 degrees, right? So then 5 is equal to 39.8 plus 15, 54.8 degrees. So the resultant force is in the direction of 54.8 degrees from the x-axis, right? The sine law, I think you have learned these things in your maths class, right? If you take this triangle, say this is the theta 1 and this one is theta 2 and this one is theta 3, you can write a over sine theta 2, this angle, right, is equal to p over sine theta 1, which is equal to c over sine theta 3, right? So this is the sine law, right? In here we know this angle, we know the length of this, right? But we don't know this angle, but we know the length of this side, right? So then we can find out the theta easily, right? So in the same way, this is the one method, right? Using the triangle law or parallelogram law, right? Also we can use the Resultant method, right? So you can try yourself and you will get the same answer if you do it correctly. So in our second example, the question tells resolve the 600 lb horizontal force into components acting along u and v axis and determine the magnitude of these components, right? So now you have a force, single force, and we are asked to resolve this single force into u and v axis, right? So you can see that u and v axis are not perpendicular to each other, right? So you cannot just resolve them, right? So here, how can we resolve this 600 force into this u and v axis, right? So easiest way is to think this as the resultant force, right? And we want to find the two forces which acts in u and v direction and makes this resultant force, right? So again, thinks this as 600 lb as the resultant force, and we want to find the two forces which acts in u and v direction and makes this resultant force, right? So easiest way is you draw the force triangle, right? So this is one force, right? And this one is another force, right? So this is a F1 and this is F2, right? So F1 and F2 forces make this 600 lb, right? So uh, this one are perpendicular, right? Are parallel to each other, right? This line and this line are parallel to each other, right? If you make the force parallelogram, right, it will be like this, right? So this angle is 120 degrees, right? So since these two lines are parallel to each other, this one should be 120 degrees, right? So this is 30, this is 120, so we know that this one must be 30 degrees, right? So this is a isosceles triangle, right? So this one is 30 and this one is 30, right? So which means the opposite uh, sides should have the same length, right? So this is the side opposite to this 30, so this one and this one should be same length, right? So we can say F2 force should be 6 F2 force should be, this is 600 lb, so F2 force should be 600 lb, right? And we need to find F1 force, right? How can we find the F1 force? You can use the sine law, right? F1 divided by sine 120, right? This angle is 120, which is equal to, this is 600 divided by sine 30, right? From here you can find the F1 force, right? So this is the how we can solve this type of problem, right? So here I have shown the problem, right? So the force in the u axis, the Fu is 1039 lbs, and the force in the Fv direction is equal to 600 lb, right? Okay, let's move to the third question. Third question says the link in the figure is subjected to two forces F1 and F2. So F1 and F2 forces, we have both magnitude and direction, right? So this is the magnitude of F1 force and this is the direction. This is the magnitude of F2 force and this is the direction, right? So we need to determine the magnitude and the direction of the resultant force using Cartesian vector notation, right? So whenever you heard the word Cartesian vector notation, which means that you should express your answer in I, J, K terms, right? I, J, K are unit vectors in X, Y and Z directions, right? But here we have only X and Y because F1 and F2 are coplanar forces. So you should express the resultant force in I and J terms, right? Because the F1 and F2 are coplanar forces, so the resultant force also on this plane, so which means that resultant force should be expressed as in I and J terms. So the question is, how can we express the resultant force in I and J terms, right? First thing that you should do is you should express F1 and F2 forces in I and J terms. So how can we express F1 and F2 forces in I and J terms, right? So if we take this, right? So I say this is my positive x direction and this is my positive y direction, right? So then I express F1 force in Cartesian vector form. How can I express? F1 force is 600 Newton, right? And it is 30 degrees from the x-axis, right? So what is the resultant of F1 in x direction? I can say F1x is equal to 600 cos 30, right? So F1 in y direction is equal to 600 sine 30, right? So if I take the F2 force, the F2 in x direction is equal to since the resolvent of this force in x direction is, it is in the negative x direction, right? So this one is negative x direction, so we can say it is minus 400 cos 45, right? F2y, it is in positive y direction, so it is equal to 400. Actually this is sine 45. Why sine 45? Because this angle is 45, so this resolvent is sine 45. So the y direction it is cos 45, right? So this is the magnitude of the F1 force in x direction, right? It's not vector form, right? So this is the magnitude of the F1 force in y direction, right? So we want to express the F1 force in Cartesian vector form, right? So what is the vector notation of this? F1 force in x direction, we can say this is the vector, right? This is just the magnitude. So this is the vector is equal to 600 cos 30 I. I is the unit vector in x direction, right? So what is the magnitude of, what is the vector form in y direction? Fy force in y direction equal to 600 sine 30 j, right? J is the unit vector in y direction, right? So this one tells you the direction of this force. This one tells you the magnitude, this one tells you the direction, right? In the same way for f2x, it is minus 400 sine 45 I, and f2y direction it is 400 cos 45 j, right? So now I can write F1 force, I can write F1 force is equal to F1x plus F1y, right? So what is the F1x? So I can write as 600 cos 30i plus 600 sine 30j. So this is the F1 force in Cartesian vector notation, right? So if I write the, if I delete all these things, so if I write the F1 force, if I write here, F1 force is equal to 600 cos 30i plus sine 30j, right? This is the expression of F1 force in Cartesian vector notation, right? In the same way, I can write F2 force equal to minus 400 sine 45i plus 400 cos 45j, right? So this is the expression of the This is the expression of the F2 force in Cartesian vector notation, right? So we want to find the resultant force, right? So the resultant force Fr, I say it is Fr is equal to F1 plus F2, right? So this is not just the algebraic summation, this is the vector summation, right? So F1 force 600 cos 30 I plus 600 sin 30 J, right? And F2 plus force is plus, put here, minus 400 sin 45 I plus 400 cos 45 J, right? So if I take the I terms together, you will get something like this, right? 600 cos 30 I minus 400. If I take the I terms together, right? This is cos 30 minus 400 sin 45. I can say I plus 600 sin 30 plus 400 cos 45 times J, right? So it is like this, right? So then if you simplify this, you will get something like this, right? So F R force is equal to 236.8 I plus 582.8 J, 0.8, we write again 582.8 J, right? So this is the answer. Fr is equal to this one, right? So we express the resultant force in Cartesian vector notation, right? This answer includes the direction and the magnitude. If somebody asks you the magnitude of this one, just the magnitude, then we can say Fr magnitude is equal to the square root of 236.8 square plus 582.8 square, right? Then you will get the answer. I think it is around 629 Newton, right? So if somebody asks the direction of the resultant force, now we can say, now your resultant force is something like this, right? So in x direction you have 236.8. So this is, and this direction 582.8 force, right? So your resultant force is like this, right? So say this is theta, and if you make this parallelogram, this is 582.8 and this one is 236.8, then tan theta is equal to 582.8 divided by 6.8, right? So theta is equal to tan inverse 582.8 divided by 236.8, right? So which is equal to 67.9 degrees, right? But this is how we can find the magnitude and the direction. But if you given the answer in this Cartesian vector form, which include both the magnitude and direction, so you don't need to find this type of things. But if somebody asks specifically what is the magnitude of this resultant force, then you can find like this, right? Like this, right? So this is how we can solve the problem, right? Okay, let's move to the last question. The example 4. The end of the boom O in figure is subjected to 3 concurrent and coplanar forces, right? Concurrent means all the forces meet at one point, and coplanar, you know that it is all three forces are on the same plane. So determine and magnitude the direction of the resultant force, right? So now you don't need to do it with the Cartesian vector notation, right? Just need to determine the magnitude and the direction of the force. If somebody wants to do it in the Cartesian vector notation, no issues, right? We can go and do, but just need the magnitude and the direction, right? So how can we do? So if we take this one, our three forces are like this, right? So I say the forces in this direction I take as plus. So forces also in this direction I take as forces in this direction also I take as the plus, right? So I'm going to find the forces in x direction. The resultant of these forces in x direction, I take this and I write as Frx, which is equal to sigma Fx, right? So this is equal to, this 400 force is on the x direction but is in the negative x direction, so it is minus 400, right? Plus then 250, resultant of this 250 in this direction is plus 250 sine 45, right? And this one again it goes through the minus x direction, so I can say minus 200 sine, if I say this angle as theta, I can say is equal to 200 cos theta, right? We know that from here it is this type of expression, right? So this is theta, and this one is 5, 4 and 3, 4 and 5, right? So cos theta is equal to 4 over 5, right? So you can express minus 400 plus 250, it's 1 over square root of 2, right? Minus 200 cos theta is 5 over 4, 4 over 5, right? So you will get the forces in x direction is minus 383.2 Newton, right? So the resultant of all these forces in x direction is minus 383.2 Newton, right? Why it is minus sign? Because we say this one has our positive x direction. So this one means that the force in the x direction is in this way, right? So that's why it is minus, right? So now we need to find the forces in y direction. I say this is the plus, right? So I say it is Fry, which is equal to sigma Fy, right? So forces in y direction, if you go back and see, you can see that here it is on the x-axis, right? So there is no resolvement in the y-axis. Why? This angle is 90, so f1 cos 90, cos 90 is 0. So this one does not have any component in the y direction, right? So we have only two forces, right? One is 250 cos 45 and 200. This angle is theta, it is sine theta, right? So we can write as 250 cos 45 plus 200 sine theta, right? So if you look at here, sine theta is equal to 3 over 5, right? So if I can write here 250 over square root of 2 plus 200 3 over 5, right? So you will get as 296.8 Newton, right? So since it is plus, we can say Fry is in this direction, right? So now we want to find the magnitude, right? So we can say Fr is equal to square root of Frx squared plus Fry squared, right? So this is minus 383.2 square plus 296.8 squared, right? So we will get answer as 485 Newton, right? Now we need to find the angle, right? The direction, right? So now we know that Frx in this direction, it is 383.2, right? And Fry is in this direction, it is 296.8. So this is the resultant force direction, right? If I say this is the angle is theta, then tan theta is equal to this one, which means 296.8 divided by the length of this side, it is 383.2. Theta is equal to tan inverse 96.8 divided by 383.2, right? So which is 37.8, right? Decrease, right? So if you take this is the positive x direction, so this angle is 37.8, which means that this angle is 180 minus 37.8, right? So which is 142.2 degrees, right?